In the videos previous to this, we looked at Barton-Savart's law and its applications, wherein we calculated the magnetic field intensity at a given point due to a current carrying conductor. Now in this video, we are going to discuss Ampere's Circuital law, which is another law that will help us to calculate magnetic field intensity at a point due to a current carrying conductor. So therefore, we are going to study two laws, Barton-Savart's law and Ampere's Circuital law, which will help us calculate the magnetic field intensity due to a current carrying conductor. So the statement for Ampere's Circuital law is something like this. The line integral of the magnetic field around a closed loop is equal to mu naught times the current enclosed by the loop. This basically is a mathematical statement. And mathematically, we write this statement this way. Integration, and we are integrating over a closed line. B dot dl is equal to mu naught I. To help you understand this statement in a better way, let us look at the scenario in here. We have a current carrying wire. The current is flowing in the upward direction and has magnitude I. Now, whenever we have a current carrying conductor, we know that there will always be a magnetic field surrounding this wire or enclosing the wire. The direction of the magnetic field is given by the right-hand thumb rule. Now, when we apply right-hand thumb rule in this particular case, the direction of the magnetic field is as shown by the arrowheads. When we look from above, it will be counterclockwise. Now, let us suppose that the magnetic field intensity at point P is B. Now, all points lying on this circle, they being equidistant from the wire. The magnetic field intensity at all points lying on this circle will also be B. Now, if dl is a small elemental length that we consider on this loop, so dl is this line, small elemental length, and dl has a direction. The direction of dl is taken to be the direction of the magnetic field intensity itself. At any point you can consider dl, over here. The direction of dl and the magnetic field intensity at that particular point will be the same. If you consider magnetic field intensity at point P, its direction will be going into the plane of the paper. At this point, it's coming out of the plane of the paper. Okay, so direction of B and dl, take it to be the same. So, dl is the small elemental length over here, and let us consider B to be the magnetic field intensity at point P. So, B dot dl meaning we are integrating the total magnetic field along this line, along this closed loop. We are integrating what is the total magnetic field we want to find out. So therefore, the total magnetic field along this line, so to say, is equal to mu naught into I. This is what Ampere's Circuital law tells us. Let us now look at one of the applications of Ampere's Circuital law. That is to find magnetic field intensity at a point due to a long straight wire. We actually have done this using Barton-Savart's law itself. The magnetic field intensity at a point due to a straight infinite current carrying wire. It's the same case actually. So, we have a long, very long wire carrying current I in the upward direction, as you can see. We want to find the magnetic field intensity at point P. So, passing through this point P, what we do is we draw a closed loop. Now, this closed loop is showing us magnetic field enclosing this particular line. And of course, using right-hand thumb rule, the direction of magnetic field will be counterclockwise when we look from above. So it's counterclockwise, such that at point P it's going into the plane of the paper, and we want to find the magnetic field intensity at point P. Say for example, point P is at a distance A from the wire. So to say the radius of this loop is A. Now according to Ampere's Circuital law, we know this. Line integration B dot dl is equal to mu naught into I. Now this can be written as, since this is a dot product, B dl cos theta, which is mu naught into I. Now since theta is 0, because I told you, where at whatever point you consider an elemental length, the direction of elemental length and magnetic field is the same. Since theta therefore is 0, we have integration of B dot dl is mu naught into I. please be careful here. I read integration of B dot dl is equal to mu naught into I. But we no longer have the dot over there since we've already dealt with cos theta. So therefore it's just integration of B dl on the left hand side. So we have integration of B dl is equal to mu naught into I. Now B comes out of the integral. Why? Since all these points are equidistant from the wire, at all points on the circumference of the circular loop, the magnetic field intensity will be the same. So therefore, since B is a constant on this particular closed loop, so therefore B comes out of the integral. So B integration of dl will be mu naught into I. Now what are we doing? We are integrating over small dls. So integration of small dls is going to give us this closed loop, that is the circumference of the closed loop, and the circumference of the circle is 2 pi a. So integration over dl gives us 2 pi a. So B into 2 pi a is mu naught into I, and thereby B comes out to be mu naught I by 2 pi a. So therefore this is the expression for the magnetic field intensity at point P due to a very long current carrying wire. If you check the expression we got for the magnetic field due to an infinitely long current carrying wire using Barton-Savart's law, you will see that this expression for magnetic field we got using Ampere's circuital law, and that expression using Barton-Savart's law, it's one and the same.